Hello, everyone. Thank you so much for joining us today for our webinar on Advanced Indexes in PostgreSQL, Smart Indexing for Faster Queries. Today, I have with us our principal PostgreSQL consultant, Chris Travers, who is going to walk you through everything that you need to know regarding indexes. And of course, he is going to give you live demos as well based on requests. So this is going to be a bit more interactive session than the normal ones. And yeah, before I hand over the controls to Chris, I'm going to just go over a few housekeeping items. This webinar is being recorded, and the recording of the webinar will be shared with you afterwards. If you have any questions, please feel free to use the Q&A chat box or the webinar chat box, and Chris will be responding to them on runtime. But we will also have a Q&A segment in the end as well. So yeah, over to you, Chris.
Um, Hi, thank you so much, Annie. So we will be talking today about advanced indexes. So it won't be everything about indexes. We will be skipping the basic ones like basic B trees. But we'll still be talking about B trees to some extent in some other cases. So buckle up. This will be an interesting webinar. Now, one thing to note is that Postgres is very advanced in terms of the kinds of indexing it can do. And um, I'm going to touch on some super advanced topics, but not go into them in too much detail because sort of, beyond this set of topics are things which are very single use, niche, and that sort of thing. Um, so just keep all of that in mind. So first of all, just in a little bit about me, I started working with Postgres in 1999, so I guess that's a little over 25 years of Postgres, maybe 25 and a half. I don't think it was in January of 2019. No, sorry, 1999. But so it's a lot of time that I've had playing around with Postgres. I've seen it develop a lot. I've seen it had all kinds of features, a few of which we'll talk about today, but many of which have been there since the beginning. Um, so um, I've worked in all kinds of environments, from as a DBA to an application developer. And so, some of these sorts of things you'll see can be as useful to understand as an application developer as you would as a DBA. So keep that in mind. So, in this webinar, we're going to cover a couple of very important topics in relation to indexes. We will talk briefly about B-tree indexes in the index class section, um, but we're going to start by talking about partial indexes and then functional indexes. These are things which Postgres has supported for as long as I've been working on it, which is quite a long time, and which solve a number of specific kinds of problems that can crop up and are actually which are actually very difficult to solve without these tools. Then we'll talk about covering and multi-column indexes, which are also very, very helpful under certain circumstances. These are newer. I remember when they were added, both of them. Then we have index classes, where we will talk about in detail the different kinds of indexes that Postgres supports. Then we'll talk briefly about op classes. I'm not going to go into those in so much detail, but you need to know what they are and sort of why they exist so that you can use some of the other kinds of indexes appropriately. So in other words, we're going to be covering most of the territory beyond the basic B tree. I will also just note at this point that Postgres is so extensible that you can add your own index methods. So, in fact, some extensions do this. We have an extension called rum, which offers an extension on the gin index type. Again, puns over alcoholic beverages, but it is what it is. And then, for example, PG Vector offers additional indexing types specifically aimed at AI workloads. So what we're talking about here is are all still general purpose index types, things that you might find generally throughout your career within Postgres. But for specialized workloads, there can be more kinds of indexes that we won't get to here. So the first thing I want to talk about is Postgres has an idea called partial indexes. Partial indexes will index a subset of a table where a where condition is met. So for example, in the first one, we could create an index on a jobs table, indexing the ID field, but only where the processed field is not true, right? So if processed is null or processed is false, we index the ID, and then when we set that to true, we just simply don't index it, and then vacuum will clean up the records, right? Um, and in this basic point, we can create a small index which covers a key segment of a table that we are querying frequently, right? Because because for example, B-tree index traversal is sort of an O log n complexity, right? Making the index small doesn't necessarily make it perform that much better, unless it is small enough that now it fits all in memory and you don't have to go to disk. So, despite the complexity limits to reducing index size, being able to get your indexes entirely on cache can be a really big win here, and partial indexes can do that. So, this is something which particularly if you have automatic jobs which run against a subset of a table, um, partial indexes can help that quite a lot performance-wise. But there's something else you can do with partial indexes. Remember that in Postgres, a lot of your constraints are in fact enforced by indexes. So, for example, unique constraints are enforced by indexes, and so are exclusion constraints. I don't think you can do this with an exclusion constraint, but with a unique constraint, you can in fact create a partial uniqueness guarantee. So, for example, suppose I have an e-commerce application, and in the e-commerce application, I have a number of different taxes that I have to track. Each one goes into its own account ID, right? And these sales tax rates can change over time. So when the sales tax rate changes, I might update the valid until the date when it stops being valid, and then add a new record with the newer rate and have it valid until infinity. Because we only want one rate that we expect to last forever, we could create a unique index on that account ID um, where valid until is equal to infinity. And this allows us to ensure a unique constraint only where specific other characteristics are met. This can actually be really, really, really helpful in enforcing integrity as much as improving speed. So partial indexes are actually something of a game changer. They can do some really cool things in Postgres that might not be evident at first. So as I mentioned before, the first one specifies an index on a hot sample in a large table. For example, I've seen it in cases where we've had large tables where you have data coming in and then it's aggregated and sent somewhere else. And so the records which have not been aggregated yet can then be flagged as not aggregated, and then you can index those records, and then it makes the queries to gather those records very, very fast. You can also do it to specify uniqueness constraints that are only affecting a part of a table. I've already mentioned that with regard to sales tax. I used to actually maintain accounting software, so it's something I've actually done in practice. The second major kind of advanced index I want to talk about here, and again, we're still talking about B trees here, typically, although these can be done on any index class, are functional indexes. And you can also, in fact, index any expression you can do in SQL as long as the function that handles the operator in the expression is immutable. In other words, the operator has to be something which always returns the same output for the same input. As long as that's the case, then we can index the output. So in the first example, you might have a notes table. You might have a notes text field in it where the main text of the note is, and we could create an index on the notes table where we index the output of taking the notes text and running it through the 2TS vector, right? And this would be very typically used in the case where we're doing a lot of full text searches. So rather than store the TS vector as its own column in the database, we can just convert it to a TS vector for indexing purposes only. And that can actually be really, really, really helpful. And then, of course, if we want to do a full text search, because we will be converting the text to a TS vector, then Postgres will know to use the index. There's a second case where you might want to extract information from a field or create a derived value that then you index. Now, these could also be unique indexes too. There's no reason you can't have even a unique partial functional index. So these are all dimensions and you can combine them together as you need to. So in the second example here, we have a documents table. In the documents table, we have a full text field. And somewhere in the middle of the text is a patent date. So if we write a function that pulls out the patent date and we mark it as immutable, we can index the output of that analysis, and we don't have to actually reevaluate it every time we want to determine what the patent date of a document is. And on top of this, we could use all of these, we could use that for ordering as well, right? So functional indexes are a little bit more complex in their use cases than partial indexes. There's a reason I started with partial indexes instead. And what it does is indexes the output of the function. So what happens is it will run the function or the expression on the row or the field within the row as it comes in. And then it will store that in the index only, right? So when you query against that expression, then we just search the index for matching records. If you want that in the return list, it will still calculate it again. But if you're not going to return it, you're only using it for ordering or searching, then there's nothing to be gained by storing it in the table separately, right? And that means that it runs the function when you insert or update, but it can skip running it on read. So if you have something that's relatively expensive to run, then this allows you to optimize so it gets run once when you insert, and then it can skip it on read unless it needs to display the result. Although that's an interesting thing where it would be interesting to see if Postgres could be changed to pull the value from the index in this case as well. But I don't believe that's supported right now. Now, Postgres has 3 volatility levels for functions. There's volatile, which means every time the functions run, regardless of inputs, the value may change. A function, for example, like random or the clock timestamp, right? And in these cases, you definitely don't want to index it because, I mean, indexing random output would be meaningless, but also if you're trying to scan it, it wouldn't be very useful because you want that to change every time you run the function. And by definition, when we're storing the output of a function in the index, then we're guaranteeing it's supposed to be the same as it was then. The second tier, which most functions are by default, is called stable. And stable functions are supposed to return the same result if they are run inside the same snapshot. In other words, if the same if the same data set is valid for isolation purposes. What this means in practice usually is that stable functions, if they're run with the same inputs, will return the same outputs in the context of the same query. We cannot index these because their outputs may change over time, and as a result, storing that and searching on the index would again be misleading and possibly wrong. So a good example there would be, let's say you have a function that goes through and it produces sums of rows from another table. That would be stable, right? On the other hand, if you have something which takes in two arguments and processes them, or one argument and processes it, and derives a value repeatably from that value, then yes, we can index it. In which case, you mark the function as immutable, and then you can do that. And then, of course, if you change the function definition, the function will you have to reindex because otherwise you'd have a problem. So those are the ones that Postgres has supported since I've been using it in 1999. Now we'll go to ones that are much newer. Multi-column indexes allow you to specify indexes from one row to another. Sorry, from one column to another. So you can have, let's say, three columns, and in a particular order, uh, they will typically be traversed. Now, one minor error on the slide is it says can search by all rows. It should be can search by all columns, right? So a multi-column index, it's far more efficient if your where clause has the leftmost columns and if you're just dropping the rightmost columns, right? Um, but Postgres can try to use an index anyway and just continue to search the index, by all values in the missing columns. It's a lot less efficient that way, but sometimes the planner will choose it in those cases simply because it believes it's better than a sequential scan of the whole table. So multi-column indexes can be used in that way, but in general, you want to have all of the columns in your where clause as far left on the column list as possible, and you want the most selective columns first. The reason is that you can think of a multi-column index is either a single value that you're traversing B-tree wise, or you can think of it as a B tree of one value connected to a B tree of the next value connected to a B tree of the next value, right? I'm not 100% sure how the internals are in Postgres. I believe it's treated as a single value, but I could be wrong on that. But if your most selective value is first, then what you've done is you've broken up the search so that it's far less complex once you get through that first column. Now, similar to multi-column indexes, covering indexes came later, right? With both multi-column indexes and covering indexes, all of the data from the columns will be available for the index scan, which means that if your select list only includes things from the column list in the index, that you might not have to hit the underlying table. You might still, because of the way Postgres tables work. Um, Maybe, yeah, I don't think I'll go into that at this point, but if people want a discussion of that, please leave a message in the comments and I'll come back to that question at the end. Um, but basically, um, in both of these cases, you can sometimes get a index only scan, where we don't actually have to touch the table if we know that all rows in a page that we're looking at are visible, right? Covering indexes work a little differently, though. Multi-column indexes have all of the columns in the standard B tree. Covering indexes put them in a posting list. So this means that these columns are not available for searching via the index, but they are available for the purpose of retrieval. So that can then also help avoid a table lookup. They can therefore be a bit faster than and more compact than multi-column indexes for the same columns. There is, however, an important limitation, which is not on the slide, which is that expressions are not supported in the posting list. And I'm not actually sure why. The documentation says that they can't be used in index-only scans, but at least from what I've been able to see, it looks like functional indexes can do index-only scans. And so in those cases, if you put them in the column list rather than the include list, then they might still work. So as I say, I'm not 100% sure why covering indexes don't support expressions or functions in the include or posting list. So now I would like to talk a bit about index classes. Postgres has a large number of index classes, and mastering indexing in Postgres requires understanding these. Um, Now, so far, we've been talking about everything that's quite compatible with just B-tree indexes. Although in certain cases, you could, of course, use those same techniques with other classes as well. But Postgres supports 5 classes out of the box. And again, extensions can add more. I mentioned stuff about PG vector, and I've mentioned some other things. I think about like rum and some other index types that are possible to add through extensions. Um, but these 5 are built in, and they are extremely important to understand. Um, Also want to discuss index op classes quickly before I go through index classes in depth. Each index, and the basic thing is that each index class or each index type, um, it's not quite accurate to say either a class or but for a given index, there's going to be a series of operators that it supports. So for example, if I have a B-tree index and I want to search for things greater than 10, and I want to get the next 10 of them, right? Then I can use a B-tree index to do that. And I can do it with basically a range search, a comparison, basically a collation comparison, an equalities, or a range search, right? And so B trees are great for that. And therefore, we think about them having certain operators that they support, right? This is true with every other type of index as well, right? Hash indexes only support equality. And um, Brin pretty much only support equality and range. So similar to B-tree in that regard. Um, but Gin and Gist support multiple different op classes, often for different types, and those op classes may support different types of operators, right? So if you select the wrong op class, it's possible that your index just simply won't be used when you expect it to be used because the internal representation and structure of the index is just simply not set up so that it can answer the kinds of questions you're looking for. So, going through the classes here, B-tree indexes are the standard. I mentioned before they can do equality and range searches. And they're the most common index type that we'll ever use, right? Um, it's very hard to beat B-trees at general workloads. They have plenty of problems, but everything else has plenty of problems too, only more. So they're the standard. Use them unless you have a reason to use something else. Treat a lot of the techniques that we're talking about here as power tools, things to use when standard B-tree indexes don't get you where you need to go. As always, being clever is not a good thing when it comes to building software and building systems. Hash indexes are equality only. My tests are that they're usually slower than B-tree. I haven't actually run into a real world case where they weren't. However, I can imagine cases where the fact that they're smaller might mean that they stay in memory more easily, and so maybe you have fewer cache misses. So there may be cases where they're faster, but it's going to be a rare case, and it may not last over time. Um, Prior to Postgres 10, they weren't even crash safe. And they weren't replicated. After Postgres 10, I think it was, then they became um, crash safe and replicated, and so they can now be safely used in heavier environments. But basically, um, if you think that they might be useful, benchmark them and benchmark them against your real world data. So now let's talk about gist indexes. Gist indexes are where we start to get complicated. GIST stands for Generalized Index Search Tree. And it's basically an interface in which you can have any tree-oriented search pattern that plugs into it, right? There's also a variant on this called SPGIST or spatially partitioned GIST, which is typically used for spatial data, but GIST is also used for spatial data. And it very much depends upon the kinds of operations you want to support. And you want to be careful about this and look at the documentation and check out the operator classes before you decide SPGIST versus GIST. Now, because GIST is a general interface, there are many, many different implementations. So, for example, spatial indexes usually work along an R-tree type structure, while if you're trying to do nearest neighbor searches with TS vectors, for example, you may have some sort of a bitmapped pattern, right? So, so because this is an interface, you have tons of different implementations. Each op class implements its own gist type behind the scenes. So if that makes sense. But historically, these are most heavily used for spatial data as well as for things like full text search. If you're saying, what about GIN? I normally use GIN for full text search. Yes, we use those too. GIN are generalized inverted indexes. They're used for searching membership. So the classical point of a GIN index is you have an array of numbers you want to search for all rows where the array has a particular set of numbers within it, right? And that should say array overlapper membership, not array overlapper membership, right? And so very oftentimes these are used for things like full text search, array overlap, membership. Um, what else have I actually seen gin indexes used for? Like another very common example is if you're indexing JSON-B documents. Very oftentimes you'll set up a gin index and then you can like you can effectively use that inverted index to search whether certain keys and values match the underlying document. So those are your main classes. Um, I forgot to mention in here Brin indexes. I'm going to mention them as well. Brin indexes are block range index notation indexes, and basically they're used um, for example, data warehousing workloads, where your data is mostly sequential, and therefore you can have indexes which will basically say, um, you know, this particular date value is only found in this range of blocks, right? And those indexes are very small. They fit in memory very easily. They help with searches very nicely. They are a bit of a pain to maintain, and but they're very useful in those kinds of workloads. So Brin indexes are another particular case. Um, Then I'm going to talk about PGTRGM just a bit. And then I'd like to open this up to general questions and answers. If you have a request for a demo, love to hear from you, and we'll go from all of this. Now, let's talk about the kind of query that everybody hates when it comes to indexing. Infix searches. In other words, select, such and such from text string where text like percent some string percent, right? You're searching for something in the middle of a string, and therefore B trees will be absolutely of no help whatsoever, right? Gin and gist indexes can be used for infix searches if you're clever. So what PGTRGM does is this is an extension that ships with Postgres. So if you're installing from packages, it might be in a contrib package. But basically what it does, it gives you gin and gist op classes for infix searches, among other things. So I can basically say I can search for a string inside another string. And what it will do is it will break it down into series of trigrams. TRGM stands for trigrams. And then we'll do a membership search on the trigram. And then for those matching rows, then we'll actually go and recheck. So in this particular case, we can we can do these infix searches using an index, and it will be much faster than doing a sequential scan if you have a big table. And um, suddenly a major difficult problem is solved. PGTRGM also supports similarity searches, or so the question is, is there a typo here? What are some similar records that we have that aren't quite the same? Um, and we can use PGTRGM for such searches as well. Again, very useful for cases where you want to find out what what somebody might have meant to type, if you didn't hit an exact result. So from here on out, I'd like to take questions and basically happy to do demos. It's hard to come up with meaningful data on a laptop for many of these indexes because you need a fair bit, but I can go through like how I would test a particular proposition. And if you have a question and you want me to come up with a test on my laptop, I'm happy to do that.
Chris, I believe maybe you can give a hypothetical scenario first, or show a test or how a demo would go about, and then we can take the
Yeah,
questions that we have.
sure.
Thank you.
Um, Hold on a second while I just change what I'm sharing. Okay, so let's do this. Let's just do PSQL. Okay. So so if I were just to go ahead and create a test here, right? One of the challenges that we have in testing indexes is you need enough data that that you're actually going to span enough pages that it's worth using the index. So for example, um, I do have pgtrgm set up. Um, if I do Northwind customers, I have a index, trigram index on company names. So if I do select star from Northwind customers, where company, actually, let me just do it this way. Like, um, I don't know if there is anything that matches here. Let's do. I'm just gonna grab something here. Let's see. Okay, so I have one record here. If I do an explain on it, it's not going to use the index. It's going to do a sequential scan. And the reason is that the table is just too small to make it worth doing an index scan. If I set sequential scan, enable sequential scan to off, and I do the same thing again, I will get an index scan, but it's not really going to help me that much because, again, the table's very, very small, right? So let me show you how I look at questions like expressional indexes. Create table. Let's create yeah, an integer primary key, and then what I'm going to do is I'm going to insert to AXP test, and then I'm going to select generate series. And let's insert a million values. The reason for going all the way up to a million is it doesn't take that long, and it will actually create a large enough table that an index will be helpful, right? So now, um, if I were to do explain, analyze, select count star from exp test, where where ID, and let's do a modulus equals 1. Okay. And what we'll see is that we get this wonderful thing where we have done a parallel sequential scan. Only took what, a little over a tenth of a second, but still, it's a lot of resources to do that, right? However, suppose I do this, create index on exp test, ID, and then, right? That's not going to work, by the way. I'm going to get a syntax error here, and I'm going to show you what the problem is. It's a little bit stupid. Um, when we add a second set of parentheses, then it tells Postgres that this is definitely an expression. Otherwise, it has trouble determining that such. So now I create the index. I'm done, and now watch what happens when I do the same. I get a bitmap index scan, and it's not a parallel process. It's a single process, and it took 1/10 as much time. Okay, so that's one thing here. Does that does that answer? So I guess that's a good basic that's a basic introduction to how I would look at these things. So yeah. Now I see a couple questions in the Q&A at this point. I will go ahead and try to go through those. If people have questions about this demo, I'm happy to answer them as well. Feel free to keep the questions coming. The first one says, "Hello, index for vector." Um, now the indexes for I assume you're talking about the stuff in PG vector. PG vector has two of its own index classes, and I haven't played around with them too much. Um, but they are very different to these kinds that we're talking to here. I would suggest taking a look at those, the documentation and the extension carefully. It is one of those areas where we have a sort of a single purpose index type. Um, I think I'm just going to double check what the names of the two index types are. I know that there are two off the top of my head. I forget what they are called. Um, basically, I mean, you can of course use gin indexes, etc., but they're not really very helpful. Same with gist. Um, but there are two other major types of indexes here. I'm just trying to double check this here. The two major types of indexes that it has are HNSW, which is hierarchically navigated, I think, semantic world, if I remember right. I could be wrong about exactly what the acronym stands for, but basically you can think of that as kind of logically behaving sort of like an R tree, right? Um, it's a multi-layer graph, and it has better query performance than IVF flat, but it has much slower build times and uses more memory. Um, it's a different approach. The IVF flat, um, trying to see, IVF flat's different. I'm not as familiar with IVF flat as I've at least thought about the HNSW stuff a bit. So. I wish I had a more detailed answer for you for PG Vector, but it's something which I only have limited experience with. The documentation on the PG Vector um, on the PG Vector extension looks pretty good. And if you have experience with other kinds of indexes, that can be kind of helpful. So the second question I see is how would I create an index on a field from a JSON document stored in a column? Now, Before we get into this, we have to note something very important. Postgres has two different ways of storing JSON documents. The first is JSON and the second one is JSONB. JSONB is optimized for indexing and it's optimized for retrieval of keys and values. The downside is that JSONB, that there are at least two cases I'm aware of valid JSON documents that cannot be stored in JSONB without losing something. The first is if you have duplicate keys, JSONB will not work. And the second one is that you can embed Unicode code points in the text string of a JSON document. JSONB converts these internally to C strings, right? And as a result, if you embed a null character, Postgres will go, can't do that, and it won't store it. So the index options here are going to be a little different depending upon what you're doing, but you're asking about indexing a field from a JSON document. And the obvious way to do that is with an expression index. I'm trying to think if I don't have a document index, I don't have a document database handy with a lot of JSON documents in it. And I don't think I have an easy source for, actually I might. Hold on one second. Suppose I do this. Table JSON test. Okay. What do I have in JSON test? Oh, looks like I have. Okay, so I have this table here where I've taken parts of the system catalog and I've just thrown them into JSON in here for testing. So you're in luck. I have something fairly easy to work with here. So now I think I'm storing this one in JSONB. So if I do, let me just do this. Okay, so I have this JSON and this JSONB. So if I want to index, let's say, the OID field in the JSON document, I would do this, create index on JSON test as JSON. And then I think I need that. And away I have an index. So if I want to do now explain, analyze, select star from JSON test where as JSON equals 1, 2, 3, which there should be none. Oh, of course, because we have the text string back. And you'll see that in fact um, we get the index used here. Does that make sense? Now I can do the same thing with the JSONB. And if I right now do it with JSONB, I get a sequential scan, and if I create the index, then I get a similar query plan. Does that make sense? So here's how you can basically index a field out of a JSON document. When indexing JSON data using GIN indexes, what's the difference between JSON bops and JSON B pathops operator classes? So the short answer here is that they support different operators. JSONB path operators focus on basically the whole JSONB path notation system, while JSONB operators um, are basically going to be um, In fact, let's just pull up the documentation here and take a look. Give me 1 second. Uh, I'll reshare this in 1 second. I'm just pulling up the documentation and then I will share here. Yeah, here we go. So give me 1 second. So here's a good example of where kind of understanding this stuff in the documentation. Okay, so this is not quite what I wanted. I want to look up the specific indexes for JSON BOps. Uh, okay, so it looks like this is discussed probably in this section here. Okay, so what you're going to see here is here we have a what you're going to see here is a discussion of these two, right? So JSONB path operators supports only these three operators, right? Um, which of course includes overlap, membership, and I think is it key exists? I have to double check what the one with the question mark is. Um, now the major thing is this is optimized for things like going down JSON path, um, JSON path queries, right? Well, JSON B ops is a more general op class, which may not be as performant, but supports a much larger number of operators. So I guess that's the short answer here. I've actually never used JSON B path ops much. I've usually used JSON B ops for most things. Does that answer the question there? If it does, or feel free to, or if you have follow-up questions on that, please ask. So are there any other questions at this point?
Yes, so Chris, I have two questions. So for
Hmm.
functional indexes, what happens if I change the function definition?
Right. Okay. So I'm trying to think about the internal representation here. I believe that functional indexes, I mean, they're definitely tied to the representation um, of the function in the system catalogs, right? So if that changes, then there's enough information for the planner to invalidate the index and stop using it, in which case, fortunately, the index will simply be ignored until you reindex. Um, the area where this could actually be a big problem, though, is if the index definition is external. So, for example, you have an index, you have a function which is in an extension in a C file, a C library, for example. And if that updates, then um, that wouldn't necessarily update the catalogs, and therefore Postgres might traverse the index and return wrong results. So that's the one case I can think of where it's a problem. Of course, you get similar problems with just straight indexes if things like your C library changes its collation, in which case you're going to get the same kind of problems. We've seen that with glibc, by the way. So as long as it's within Postgres and you make the change there, Postgres is smart enough not to use the index until you reindex.
All right. Thank you so much. And last question. In this scenario, can multi-column indexes really speed up queries?
So multi-column indexes. So probably the case that comes to my mind is I was working on a project in Denmark, and we were still on Postgres 9.5, so we didn't have a lot of the tools we do now. We didn't even have covering indexes. And one of the requirements was to implement row level security by hand, since that wasn't in the software yet. Um, and so we had permissions attached to two tables, and then we had a whole bunch of tables in the middle that people might query, but we had to always check permission on both of those tables on the other sides, right? So the idea is if somebody's working on bringing something to production and it needs to be hidden, we need to be able to exclude those rows from the queries. And so we had views and everything to do this. The problem was adding all those joins is slow, right? And while we had of course, primary keys have their own indexes and we had all the foreign keys indexed, that still meant you go through the primary key, um, or you go through the foreign key, you look at the table, you go get the primary key, then you repeat on the next table and this sort of thing. So in those cases, if we put the primary and foreign keys in the same index, right? Then we could turn that three-stage process into a one-stage process and it really sped up the whole system, right? Because um instead of looking up like multiple different things in different places, we could get them all in the same index lookup. So that's a good example. Like especially if you are just joining tables to traverse them and get something on the other side, multi-column indexes and covering indexes can be really, really helpful there.
Thank you so much, Chris. Really appreciate the detailed answer. And yeah, I think we can wrap it up for today. So thank you so much, Chris, again for this insightful presentation. Thank you everyone for joining us. We have an upcoming webinar on 25th of February, which is going to be focused on PostgreSQL query optimization. I have shared the link in case you're interested in registering for that. And yeah, that's it from our end, and have a wonderful rest of the day. Goodbye.
Thank you.